So, in the last lecture we have actually started introducing you with combustion processes, and in this lecture, which is a follow up of the last lecture, what we are going to do is we are going to understand theoretical combustion process and an actual combustion process. That means, what is the difference between a theoretically complete cycle as opposed to an actual combustion process. So, let us see what are the main differences. So, as you will recall, you have a fuel which is a hydrocarbon, which let us say represented by CnHm, and we have air as the oxidizer. It goes inside the combustion chamber, and naturally if you want to completely burn, complete burning means if all the carbon in the fuel burns to carbon dioxide, all the hydrogen burns to H2O, and for example if there is anything else, let us say sulfur, it burns to sulfur dioxide. Okay. We will call this as complete combustion. That means you get, in this example there is no sulfur. If there was a sulfur, then you have to take that also into account. So, you will get, if you balance this equation, you will get n moles of CO2 and m by 2 moles of H2O, and naturally if you had used a lot of air, okay, which was so some part of oxygen has gone in forming CO2 and H2O, but there may be excess oxygen also. And as you will recall, nitrogen is inert, nitrogen does not take part in the combustion process. So, nitrogen will also come out as a product. So, the reactants will burn inside the combustion chamber, they burn completely. Okay. So, whatever are the combustible components of the fuel, they are burned to completion, that means they are fully oxidized, so to say, and you will get CO2 and H2O. Now, suppose for some reasons, okay, we will talk about what reasons, this combustion is not complete. That means there are certain molecules, let us say of hydrogen, which are remaining here, for example. There are certain molecules of carbon monoxide which are remaining here, which have not converted to CO2, or for example there is also some unburnt free carbon, let us say soot, okay, for example, which we call as soot, for example, unburnt carbon particles, okay, they are also here in the products. That means if the combustion products contain any of the unburnt fuel or components such as carbon, such as hydrogen, such as carbon monoxide, or you can also have hydroxyl ions, for example, which may react with something else later on. That means the idea is that many of these unburnt compounds may subsequently burnt after coming out of the combustion chamber. For example, in an automobile, some CO or some carbon monoxide or some unburnt carbon may catch fire, let us say in the silencer or in the exhaust manifold, for example. Okay. So, the reaction of conversion of CO to CO2 may continue outside the combustion chamber, but as far as the combustion chamber volume is concerned, this particular control volume which is of our interest, we will say that inside the combustion chamber the combustion was incomplete. That means there was an exhaust which came out of the combustion chamber, which was not completely oxidized products, but it was also containing some of the unburnt elements or unburnt molecules, that means which still can oxidize. If they oxidize outside the combustion chamber, whatever energy is released by this incomplete combustion, which may lead to complete combustion outside the combustion chamber, that energy will be lost actually as far as this combustion chamber is concerned, because we are extracting the heat only from here. Whatever post exhaust reactions, they always take place. Whatever happens to this exhaust gas, if there is an unburnt, let us say incomplete combustion or incomplete combustion products are here, that enthalpy will be essentially lost. So, you have to differentiate between theoretical combustion, that means a theoretical combustion is one when you get sufficient air. So, let us come to that. So, before that, what are the reasons for incomplete combustion? Let us say there is insufficient oxygen, that means you actually have a lot of fuel, but your oxygen content is low, that means or the air content was low. So, many times you have seen in a truck, for example, which is heavily laden with cargo, and it is giving a lot of soot, okay, a lot of black smoke comes out. So, that black smoke essentially is coming out because the diesel is not completely burned and some of the carbon particles are still remaining incomplete, and since there was probably insufficient oxygen, that is one reason, or there was insufficient mixing That means the liquid droplet came into the combustion chamber, the diesel fuel did come into the combustion chamber, however it did not mix. That means the fuel did not have oxygen molecules around it, and it was the combustion chamber, there was probably limited time because the engine is running fast, and by the time fuel could not completely burn inside the combustion chamber, and therefore there was limited time, and the exhaust valve opened and the unburnt carbon actually came out as soot. Okay. So that is another issue. The third issue can be dissociation. That means some of the oxidized product can go back, because at high temperatures the reverse reaction can take place. So we will discuss dissociation in detail when we are talking about equilibrium and things like that. So at that time I will explain you that how let us say the forward reaction, let us say C plus O2 gives CO2, and then the reverse reaction can also start. That means these molecules can again dissociate into carbon monoxide and oxygen, for example, or carbon and oxygen in the reverse reaction. So dissociation may also take place. Usually as far as the hydrocarbons are concerned, the oxygen has a much greater tendency to combine with hydrogen than it does with carbon. Therefore, you will see that in an hydrocarbon, the hydrogen is typically always getting converted to steam. Free hydrogen is not so prevalent as compared to on a comparative basis to free carbon, for example, in terms of soot or carbon monoxide emissions which come out due to incomplete combustion in an IC engine. Typically the hydrogen which is there in the fuel gets usually converted completely to water or steam, for example in hydrocarbon combustion reaction. The hydrogen in the fuel is normally burns to completion, that is what I have stated here. So remember, insufficient oxygen, insufficient mixing, insufficient time or limited time to burn, and dissociation typically at higher temperatures, that is the reverse reaction, they are responsible for let us say incomplete combustion. Now we will define the term stoichiometry or stoichiometric combustion or stoichiometric mixture or theoretical air. So what is theoretical air? That means the minimum amount of air which is needed for the complete combustion of a fuel. So let us say we have methane, for example. Okay. So methane, if you take 1 mole of methane, okay, there is a theoretical amount of air which is required or oxygen which is required to oxidize it completely to CO2 and H2O. So 1 mole of methane will naturally give 1 mole of CO2, and it is H4 here. So if you balance the equation on both the sides, you will get 2 moles of water, so 2 H2O. So to get this, to balance the equation, you get 2 multiplied by 1 mole of oxygen and 3.76 mole of nitrogen. So for every 2 moles of oxygen, you will get 7.52 moles of nitrogen as part of the mixture of air. Okay. So this is air. Okay. So 4.76 moles of air will be is represented within this parenthesis, for example, and naturally the nitrogen does not react. So whatever nitrogen you have on the left hand side of the equation, you will get that in the right hand side. And what we have done here, we have done a complete combustion, that is no unburnt fuel is remaining, there is no carbon monoxide which comes on the right hand side, there is no let us say free carbon which is there on the right hand side, there is no free hydrogen which is there on the right hand side, and so there is no free oxygen also remaining in the right hand side. That means just about enough air which gives you sufficient oxygen that this particular methane molecule is completely burnt to CO2 and H2O. So there is no free oxygen in the product. So therefore this particular, let us say, requirement, this is the minimum amount of air which is required. So this minimum amount is called as the stoichiometric requirement for 1 mole of methane. Okay. So the stoichiometric or theoretical combustion is that combustion process, the ideal combustion process during which a fuel is burnt completely with theoretical air. So of course whether this happens in reality is something which we have to see. What are the factors, in spite of the fact that you give let us say theoretically correct air, you will see that it is possible that complete combustion actually does not take place because of the reasons which we have just outlined. Dissociation may take place, or there is not enough time which is available for the combustion to take place inside the combustion chamber, and therefore the exhaust gases which come out of the combustion chamber are not CO2 and H2O, but there is some amount of oxygen is also available in the exhaust, because not all the oxygen was used up to make CO2. So for example, some CO may also come. So therefore, unless we define a basis, that means unless we define what is theoretically correct, we will not be able to analyze the real time systems. So the real time systems will have unburnt fuel, it will have several products of combustion which are away from CO2 and H2O. There may be carbon monoxide, there may be free carbon, there may, if sulfur is present, then sulfur dioxide may form. However, free sulfur may also be available, or other oxides of sulfur may also form. So complete combustion does not take place, incomplete combustion takes place, and therefore stoichiometric air or theoretical combustion we have to use to benchmark all our subsequent analysis. So you require certain theoretical air, and then what actually happens in the engine? Are you giving theoretical air, or are you giving a little more air than what is required? So that is what we are coming next, that is the excess or the deficient air. So for example, if the amount of air is in excess of the stoichiometric amount, so let us say you require, let us say 4 moles of air, okay, or 10 moles of air, and what you are supplying is 25, okay. So then in the combustion chamber you are actually giving excess air. So usually expressed in terms of stoichiometric air as percentage excess or percentage theoretical air. So for example, 50% excess air means 150 theoretical air. That means 50% excess means over and above the stoichiometry you are supplying more air, okay. And there are several reasons to supply more air, for example, okay, which we will discuss subsequently, because if the time availability is less, you want to increase the probability that every fuel molecule actually encounters an oxygen molecule in close proximity in the given time which is available, and therefore you may like to supply a little excess air. There are other reasons also for supplying excess air, or let us say deficient air. You can also have deficient air. So the amount of air which is less than the stoichiometric amount, which is often expressed as percentage deficiency. So if you have 90% of theoretical air, that means it is 10% deficiency. That means whatever is required, you are actually given 10% less air. So naturally you can have 10% by mass or 10% by volume, but that is usually stated. If the stoichiometry is given in molar terms, then it will be specified whether you are discussing mass basis excess air or deficient air, or molar basis excess air or deficient air. So that will be made clear to you when you look at the problem, for example. Now what is equivalence ratio? Another new term, the ratio of the actual fuel air ratio, that is the actual which you are supplying, to the stoichiometric fuel air ratio. So naturally, if the actual fuel air ratio small, then you will have an equivalence ratio which is less than 1, and if the actual fuel air ratio is more, then you will have an equivalence ratio which is more than 1. So sometimes you are given a situation which is mentioned or expressed as excess air or deficient air, or sometimes you are also given the equivalence ratio. So both are nearly identical. You can use either of them to get the exact condition in which the fuel is supplied with respect to the air, or the air is supplied with respect to the fuel, whether it is stoichiometry. So naturally, when the stoichiometric ratio is supplied, then the equivalence ratio will become equal to 1. So it can be less than 1 or more than 1. So here is an example of incomplete combustion of propane, for example. Okay. So if you say complete combustion and you start with 1 mole of propane, C3H8, okay. So you will see C3H8 requires oxygen, and in this case we have taken pure oxygen, not air. But if you take air, then if you take a bracket here, then there will be 3.76 nitrogen which will be inside the bracket if you want to burn the same thing with nitrogen, and of course nitrogen will come out on the right hand side, okay, of the product. So C3H8 oxidizes with oxygen. So you are doing complete combustion, and it is a pure hydrocarbon. So you will do CO2 and H2O, and of course when you balance, you need 3 carbon atoms here, so you put 3 moles here, so you get 3, the carbon is balanced, and then you have 8 atoms of hydrogen, Since it is H2O, you will put a 4 here, which is 4 moles. So 4 to the 8. So you have the balanced, and now you can count the oxygen which is required. So you have 6 atoms here and plus 10 atoms. So 6 plus 4, 10 atoms of oxygen. So O2, which is the natural state of oxygen, the molecule. So you will have 5 moles of oxygen. So this is a complete combustion. Now sometimes, let us say if you take 2 moles of propane, so for complete combustion you require 10 moles of oxygen. But in this case you have given less oxygen. That means for some reasons either less oxygen was supplied to the combustion chamber or less oxygen was available at that moment of time for 2 moles of propane. So now what you see is you not only get carbon dioxide and steam, but you are also getting some let us say carbon monoxide and some free carbon. Now this is an example what exactly will happen in a combustion chamber. Sometimes it can happen that even if you get excess air, that means let us say you give 10 oxygen or 12 oxygen or 15 moles of oxygen, even then depending on the condition under which the combustion is taking place, you may see that combustion has not gone for completion. That means you may see some carbon monoxide in the exhaust or some soot particles may come out. How do you know what is coming out is very difficult to, it's not a straightforward calculation because a lot of let us say chemical reaction kinetics is involved, the time availability is involved, and then of course transport phenomena is also responsible for let us say freezing a particular let us say reaction or starting a dissociation reaction, for example at a certain temperature. So several things are responsible which will lead to a situation where incomplete combustion takes place. So the predicting the composition of the products is relatively easy when the combustion process is assumed to be complete. But then this assumption is not always true, as we all know that we do get incomplete combustion. With actual combustion process, you know, for example, I have given a photograph here where there is a burning taking place inside a combustion chamber, and you can see there is a very strong velocity inside, local pressures are different, the local temperatures are different. The piston may be cooled slightly differently than the let us say cylinder liner. Then the oxygen mixing, the concentration of oxygen inside this combustion chamber may not be uniform. For example, some portions may be fuel rich, some portions may be oxygen rich, and therefore there is a very likelihood of incomplete combustion to take place inside this combustion chamber, for example. And then when in a real time engine, the only alternative which we have is, for example, to measure the amount of each component in the product directly. So these are typically done by exhaust gas analysis, which we will take up in a different lecture. But for this lecture, it suffices to tell you that in an actual engine, it is not so straightforward to actually predict the composition of the products. So we will apply some thermodynamic models, some equilibrium models. We will do some abstraction to find out what are the products of combustion. Typically the best let us say estimate can only come if you for example measure the amount of each component as soon as it comes out from as soon as the exhaust valve opens, these gases come out, and then you can take a sample of this gas online. Nowadays online sampling is possible, and you can take an online sample here and try to get the composition of this exhaust. It is extremely important to know this composition because this is the gas which is going to the atmosphere, and therefore we must understand whether carbon monoxide is getting released or sulfur dioxide is getting released or nitrogen oxides are getting released. So what is the composition here? It is a very, very important parameter, and this composition, as you will see, it depends on the combustion dynamics inside this combustion chamber. How much time was available for the inlet valve to open and close, to what are the temperature distribution, what is the cooling close to the cylinder liner, what is the type of cooling which is provided to the piston, for example, are there leakages occurring because of which the pressure and temperature is not getting proper this thing, how is the flame getting spread from this spark plug in the entire combustion chamber, what is the clearance volume, what type of mixture, how much air and fuel came inside the system from the inlet valve. All these are very, very important parameters which will determine what type of exhaust will come out from this particular apparatus. So, with this we come to the end of this lecture. In this lecture we have studied about stoichiometry and chemical balance. So, I urge you please go back and revise how to balance chemical reactions, and we have also noted that although theoretical calculations will tell us what is the correct stoichiometry, and from there we can get the heat of reaction, for example, per unit mole or per unit mass depending on which units we are using of the fuel which we are burning, but then in reality that much enthalpy may not be available because there is a difference between theoretical combustion, which can in a typical thermodynamic system you can give infinite amount of time for this reaction to take place, but in reality there are several constraints by which incomplete combustion may occur, and therefore it is very important for us to understand the difference between theoretical or stoichiometric combustion and incomplete combustion.